So far, in what we have learned, we are always working with the Gauss-Markov model, which is y equal to x beta plus epsilon. And the main assumption on epsilon that we are putting is that it is Gaussian. In the Gauss-Markov model, the Gaussianity assumption is not explicitly there, but for most test of hypothesis, etc., we do put the Gaussianity assumption, mean 0, and variance is sigma square I, the homoscedastic assumption. Now, in many situations, this is not adequate, and we need to depart from this. And one of the most important ways by which we depart from this model is we replace this sigma square I by a general form, which is I write as capital sigma theta. So in this case, this capital sigma is a known function, and the theta are some new parameters based on which you are computing your covariance matrix. So you are postulating a different form for the covariance matrix. The particular example that we had earlier, that is the Gauss-Markov assumption, is also a special case of this, where the capital sigma form is a constant times I, and that constant is what we are calling theta here. So sigma square was the only theta parameter. So in general, theta could be a vector. You see, I put this vector notation, so there could be multiple parameters. Now, one restriction that we always have to put is that this sigma theta must be a PD matrix, and that imposes some rather complicated restriction on the possible values that theta can take. The first type of form for my sigma theta matrix is what is called a scalar matrix, where we have all the diagonal entries same, sigma square, and all the off-diagonal entries are 0. So this is our familiar form in the Gauss-Markov setup. The second form is what is called a compound symmetry structure. It is basically a structure on the correlation matrix. So I have taken the sigma square out, and this is just the correlation matrix with all the diagonal entries 1, but all the off-diagonal entries are equal to some value rho. So all the correlations are equal. Now it requires some special kind of restriction on rho for this matrix to be positive definite, and that restriction will involve the order of the matrix. So it might be of some interest for you to try to compute what is the possible values of rho under which this will be a positive definite matrix. The third form that we are going to discuss is the autoregressive or AR1 form of covariance matrix. So in this case, the form is this. Again, it's a condition on the correlation matrix. I have all the diagonal entries equal to 1. All the super and sub-diagonal entries are rho. Then the diagonal entries 1 removed from that will be rho square, then rho cube, and it goes on like that. This is called the autoregressive 1 structure because of some reason which has to do with time series analysis, and we are not going to go into that. And again, you need some suitable condition on rho such that this thing is a positive definite matrix. And then of course, we can have an unstructured matrix, that is just any PD matrix. So all the entries of our covariance matrix may be just free to move, except that we must guarantee that the entire matrix is a PD matrix. So that is also another possible sigma theta that we can impose. In this case, all the free entries of my matrix will be the components of my theta, that is the covariance parameters. And finally, you can mix or match. So what you can do is that this is your covariance structure, this is your covariance matrix, and you can take it to be a block diagonal matrix where the different blocks are of the different types of structure that we have discussed. So it is quite possible that this one, this pink one, this magenta one, is possibly compound symmetry. Then this one, the cyan one, is possibly of scalar type. And these little things could be of some other things, a compound symmetry, and this could be of AR1 type. So you can create quite complicated types of quite complicated types of such covariance matrices by combining the different component types.